two models of the universe: the geocentric model, where the world is positioned at the centre of the universe, and the acentric model, which basically maintains that the universe is so big that it doesn't have a centre. There are also two models concerning how and why we exist. There's the creation model, that everything was created by God, and there's the evolution model, that everything just happened by chance. These two areas of research and knowledge, cosmology and cosmogony, are closely related, as you might expect. And one of the aims of this talk is to highlight that particular relationship. We're going to start with this globe of the world, which I'd like you to imagine doesn't have a map on it, but it's just a sphere. This sphere will be of a particular size, radius. It has an axis which it can rotate about at a particular rate. First of all, we want to imagine that the radius of this sphere is one astronomical unit. An astronomical unit being the distance from the centre of the Sun to the world, which we are taught is about 93 million miles. If that were the case, then the centre of this sphere, at the centre, would be the Sun, and around the equator would be the path of the world's orbit as it goes around the Sun annually. So in other words, this would slowly rotate, taking 365.25 days to go all the way around. If that were the case, having measured this circumference as 94.5 centimetres, if that were the case, if that were one astronomical unit from the centre to the circumference, then the closest star, Proxima Centauri, would be 25.25 miles away. And most of the stars would be 50, 100, 200, even thousands of miles away. One of the brightest stars in the sky, for example, would be 7,060 miles away. Now, if we take this scale and we assume that we place the world upon this equator, going around its orbit around the Sun, the size of that globe would then be 12.8 microns, which is just over half the width of a human hair. So if I would pluck a hair out of my head, cut it down the middle, and place it on here, you wouldn't see it, of course. It would be very insignificant, and it would be just an invisible dot, which is going slowly around here, with the nearest star 25.25 miles away. So in this scenario, we are nothing but insignificant specks upon an insignificantly small dot on this particular equator, going around a humdrum star at the centre of the sphere, while the other stars are hundreds or thousands of miles away, and everything else is just void and seemingly pointless and hostile. Nevertheless, this is the acentric evolution idea that just about everybody is taught in the schools, colleges and universities. Now, the world on which we live, which remember that in our scale of things was the width of half a human hair, rotates in the heliocentric system once a day, or once a sidereal day to be precise. And if you try and take a picture pointed at one of the celestial poles from a darkened area, you get these circular star trails about the pole. this shows that either the universe is rotating around the world, or that the world is rotating on an axis. And as I say, what we're taught is the world rotates on an axis. So if that tiny little thing, the width of half a human hair, is rotating once a day and causing the appearance of the stars to form perfect circles, then we can assume that because the stars for that human hair are hundreds of miles away, and for this solar system model they're still hundreds of miles away, if that world is rotating around the sun, then the appearance over 1 year as opposed to 1 day is also going to demonstrate circular or approximately circular star trails over that period. If we now return to the computer simulation, we have depicted here the two axes. The world is in the middle of the universe, and we can view it either way, depending on whether we believe the heliocentric idea or whether we opt for a geocentric model. We can still model it this way, with the world in the centre. The stars are going around. We've got an axis here, which goes to the North Celestial Pole, and of course the South Celestial Pole. And those star trails that you saw in the last picture are formed in the heliocentric model by the world rotating. Here the world is fixed and the universe, the stars are rotating, but we can imagine that the stars are fixed and that the world is rotating. So when we look towards the North Celestial Pole, we see in either model those star trails, those circular star trails. And that's formed by this rotation about that axis. And if we lived in the southern hemisphere, we would see similar star trails. In fact, that picture that was just displayed was taken in the southern hemisphere, and that is these trails that are formed about the South Celestial Pole. So we have the celestial polar axis, but we also have another axis there, that red one. And that is called the ecliptic polar axis. Now, either the sun goes around the world or the world goes around the sun. But either way, for the case of modelling, it makes very little difference. The fact is that the sun, if it went around the world, would follow that path. It would actually be closer in than that, because this represents the edge of the universe. But nevertheless, it would follow this path around the world. And conversely, if the world went around the sun, then it would follow a similar path, which would be inclined at the same angle, 23.5 degrees, to the plane of the celestial equator. So basically we've got something going around that orbit there, the ecliptic, annually, and we've got some rotation here, daily. The daily rotation causes the star trails about the celestial polar axis, but in exactly the same way, the annual rotation should cause another set of star trails about the ecliptic polar axis. So to recap, our globe, which is half the width of a human hair, if it rotates, it causes the star trails about the North Celestial Pole, South Celestial Pole. Also, if that speck that is the width of half a human hair is going around the sun annually, then that is also a rotation. Both are spheres, both have a radius, both have a period of rotation, but they are inclined to one another. So the axis of rotation in one instance is different to the axis of rotation in the other. But the method of producing the star trails is exactly the same. It is a sphere, it has a certain radius and a period of rotation. So, as well as getting a rotation around those poles, we should also get rotation around these poles over a different period. We will demonstrate now that that is not in actuality what we observe. We'll move ourselves above the north celestial pole. Now notice the clock and the date. The clock is going 1 minute at a time. So this is a view of the universe 1 minute in 1 minute increments. Notice where the rotation is. We are above the north celestial pole, and the rotation of these stars is around that celestial polar axis, just as we saw in the photograph. Now let's move ourselves back to the celestial equator. And we will change the period of rotation now to 1 sidereal day at a time. The sidereal day is 23 hours, 56 minutes, 4.091 seconds. Now something is rotating every sidereal day. Either the universe is rotating or the world is rotating. No matter which one it is, if you looked at the heavens 1 sidereal day later than you last looked at the heavens, all the stars would be in the same place. The planets would have moved, the sun would have moved, the moon would have moved, but the stars would be in the same place. Here we're going 1 sidereal day at a time. Because it's not exactly 24 hours, that explains why this time increment is changing. But the stars aren't changing. Now let's take it to 1 solar day at a time. Notice now that the time isn't changing because it's 24-hour increments. So the next 24-hour increment will be 07, 43, 32, but the next day. That's why the day is changing 1 day at a time. So in other words, we can go through this model until we've gone through 365 days, and we see how the heavens have moved in that period. Notice still that the rotation is still about that axis. There appears to be here a precessing gyroscope. But that's an illusion. That plane, the ecliptic plane, is just moving around with the celestial sphere. And the north ecliptic pole and the south ecliptic pole are just like other star positions on the sphere. Now what we're going to do is we're going to take various things off and concentrate on the stars as we do so. So first of all, if we take off the celestial equator, we'll also take off the celestial polar axis. Now we'll take off the reference grid. You notice that we're still going 1 solar day at a time. So what's happening is that the day field is incrementing, and that the motions of the heavens are still exactly as they were before. So finally what we need to do is to move ourselves back above the north celestial pole. There we are. We're just above Polaris. Days are still going 1 day at a time. The stars are still rotating. But notice what axis they're rotating about. they're rotating about the same axis they're always rotating about, that is the celestial polar axis. This ecliptic polar axis is just moving around with the heavens, and no star, none of them, are rotating about that axis over a 12-month period. In other words, there is rotation about only one celestial axis, whereas if the heliocentric idea was correct, there must be rotation about two axes, because the world in that scenario not only rotates about its own axis, but the plane of the ecliptic is inclined to the plane of the celestial equator, and therefore over a longer period of 12 months there would be rotation about the ecliptic polar axis. We can therefore conclude that the heliocentric system is incorrect. And if we can get the lights on, it seems to be quite impossible in either scenario. So to conclude, we started this talk, this presentation, by emphasizing the two different models of the universe and the two different explanations as to how and why we exist. And we said that there was a link between the two. We've demonstrated via this computer simulation the fact that the heliocentric model does not explain reality. It doesn't explain the fact that we only have rotation about one axis. The heliocentric model should predict rotation about two axes. Since the heliocentric model is a special case of the acentric model, then we are justified in removing the acentric model from consideration and proposing the only explanation of what we see to be the geocentric model. However, if we do that, of course, we then have a very, very special position, because we are situated on this world, which is no longer a planet wandering about all over the place, but is fixed at the centre of the physical universe. The physical universe then is designed to go around it, to encompass it, and therefore we have gone from being an insignificant speck on an insignificant piece of rock hurtling around an insignificant star in an insignificant galaxy, etc., to being still pretty small, but nevertheless occupying the prime position in the physical created universe. And that, I believe, is perhaps the strongest conclusion of all to draw from this. We could get to that.
Apologies there.